So I changed my location today, and we are going to discuss operational amplifier. As you can see in front of you, it is written operational amplifier. So today we are going to, in this video, we will go with the detail in operational amplifier about its characteristics, about its functions, how it is going to work, and even in this video you will see the numericals also, right? And you will see the equations also, formulas also, in which you can note it down and you can use it for your work and your future reference, right? So I'm Dr. Kamalkar Sharma, your guide, your mentor. Every time I say these words because I really mean to be. So we are going to start the topic on operational amplifier. Let's start. So if you're talking about operational amplifier, what operational amplifier is? If you say operational amplifier name suggests that it is amplifier which deals in operational work or operational functions. So how many operational functions we are having? You can see towards me that addition, subtraction, multiplication, and division. So all this even integration, differentiation. So we will take care of all those operations in one amplification. Amplifier, that is why it is known as operational amplifier. So these contents we are going to discuss today. Operational amplifier, symbol of operational amplifier, what is pin diagram, what is block diagram, what is been working principle, difference between practical and ideal op-amp, and the short name is of operational amplifier is op-amp, application of operational amplifier and equivalent circuit. So you can see the full form of op-amp with operational amplifier. So in basically the terminology is we normally name it op-amp. Op-amp is basically previously called and used for mathematical operations, and it is a direct coupled. Please remember there's a difference with coupling and cascading. Coupling is means when you're adding two different things, two blocks, okay, and there is no element in between. So we say it's cascaded. If there is some element, it can be inductor, it can be capacitor, it can be resistance, it is will be coupled. So it's a direct coupled and high gain voltage amplifier. That means one thing has to be clear in your mind. It's an amplifier which is going to amplify voltage, not current. So the voltage amplifier. And high gain means output by gain is nothing but output by input, right? So it uses a differential amplifier which amplifies between input. So that means we are going to have more than one input. Let's see. It's a solid state device capable of amplifying DC and AC input signal. So it can be used for both AC and DC, right? Consume very less power, used in the field of communication and all. So it was introduced very early in 1940, and the IC number that you need to remember, that is 741 IC. Okay, 741 is IC number. So we use of transistors, we use MSI, medium scale integration. Sometimes we use LSI, large scale integration. So this kind of VLSI we normally use for making op-amp. So we normally modern op-amp works on very lower voltage, and it increases the amplitude of a signal. Please understand this. It is not going to change anything in the signal except its amplitude. So this is a symbol you can see op-amp, two inputs, one is inverting, one is non-inverting. Here I want to just emphasize that when we say inverting terminal, it means that your signal is going to have 180 degree out of phase. Non-inverting, it will remain same, but yes, it will amplify. We are having plus Vs, minus Vs. They are a positive voltage, right? So positive voltage and you can say source, right? It is going to connect with the ground. So two input terminals, inverting and non-inverting terminals. You can see the circuit symbol. Now you can see the pin diagram. We are having 8 pins out of it. First is offset null, then we have inverting and non-inverting input. Then we have a negative and positive. You can see V negative and V positive, that is 4th and 7th. And offset null. Offset null, basically sometimes student ask me, so what is this offset null is? Offset null is basically that to keep your output voltage 0 if the inputs are same. That is basically means by offset null. We have NC that is not connected, so it will remain not used if it is not going to connect, right? So you can see that in a different way the power pins are labeled, but you can see we are having a groove over here. So groove means on the extreme left hand side we will have first pin and it will go like this for 4th, 5th, 6th, 7th hits, right? So pin offset null, very clear. It amplifies the difference in voltage between the two input terminals. In fact, it should be 0 volt if the inputs are equal voltage. So from this we are having CMRR also, common mode rejection ratio. Inverting input we know very well, where the positive part of the input signal we are having amplify. So I'm going on slide mode so we will be able to see more precisely, right? So if inverted, similarly where the positive part of the input signal where we want amplification, and if not inverted. Offset null, I already explained to you. It is basically to maintain a balance between the input voltages. Output is pin 6 fixed, pin 7 receives the positive DC voltage. And similarly, V negative, when we said P negative, it will come later. So it will show negative DC voltage, right? Single-ended input. When I say single-ended input, the op-amp, that means only one input would be used. It can be inverting, it can be non-inverting. Both cannot be used, right? So input signal is connected to one input. Say now in this figure, if you see the positive is connected, that means non-inverting mode is active and inverting mode is not active. Other would be connected to the ground. You can easily see the output is A into V1. It can be V2 also. Like in the earlier case, it would be V2, V1, V2 also if the one is grounded. Now it's a double-ended input in which the input source is connected between positive and negative. Okay, so using double inputs. So differential input and common input. This question was asked in many interviews, even in question paper, it can be asked. Concept of differential input and common input. So when separate inputs are applied, the resulted differential signal is basically differential input. But when both signals are applied, okay, and two inputs can be defined the average sum of both. So please clear it. See, in both cases, two inputs would be given. If the both inputs are same, then we come to CMRR, right? But if you're taking a difference of both of them, it would be known as differential input. But if it's a common signal, because both signals are same, so we will take an average of both signals. We will come to properties of op-amp, then you will see bias current also. So that two signals will be taken as common input. So properties of operational amplifier: very high differential gain, already discussed with you. High input impedance, low output impedance, provide voltage changes, only amplitude of polarity, used in oscillator, filter, instrumentation sometime, and very high gain by multiple stages. You can see the block diagram of op-amp. First, we have input stage in which we are having inverting and non-inverting. Then we are having an intermediate stage, then level shifting stage, which is going to up and down the amount of voltage. Then it's the output stage. Working of operational amplifier, very clear. That input stage is differential, taking a inputs of a difference of both inputs. Then as the input stage provide differential input frequency response, keep to the down value. And see, amplification means your signal at the input side should be less. It would be less only if your input impedance is high. So for operational amplifier, your input impedance has to be high and output impedance has to be low. I hope this is clear. Yes, please tell me. So input stage is differential amplifier, right? It would provide two stages and provides differential input and frequency response down to DC, right? Then we are having more stages of gain, your operational amplifier. Second stage, the high gain voltage amplifier, and final stage, the output amplifier. So the actual circuit is a meter follower, which is going to have collector configuration, and output stage should allow the operational amplifier to deliver several milliamperes to a load. This means only we are having majorly three stages. One is your input stage, second is your gain amplification, and third is your output. Right. So operational amplifier can be used with first mode differential inputs. Both terminals are used. Right. So we will talk about inverting and non-inverting amplification. But in total, we are having two configurations. So remember, one is open loop, one is closed loop. So you will see open loop and closed loop. You can see I am giving V1 and V2, two inputs I am giving over here, but there is no feedback, right? So if we apply two signals at inverting and non-inverting both terminals, so it will amplify. The operational amplifier will amplify, but it amplify the difference between the two input signals. That's why it is known as differential amplifier. I hope this is clear. So that open loop gain will remain constant. So in this case, one thing has to be remembered: the V1 and V2 not have to be equal. If they are equal, then overall input would be 0, right? So see, in an ideal condition, there might be some imbalances in an op-amp. So open loop gain has to be very high. If it has to be high, that means it amplifies a very small difference in the input voltage. Then only the gain would be high. So that means your V1 and V2 has to be having a very small difference. This is only possible when both are equal to each other, but with a margin of very small. Say one is value having 35.6 and second is having 35. So there's a difference of 0.6 and it would be amplified. I hope this is clear. But on the other case, a closed loop configuration, there is a feedback. You can see a circuit in which I am giving an input, R input, and I am giving a feedback circuit also, RF. Right? So this feedback part feeds the output signal back to the input. Clear? And other one is input signal, other is a feedback signals. Two signals are taken out and one is grounded. Two signals will be taken care. Like in the earlier case, open configuration, if you remember, two signals were given. In this one is the input signal, other is a feedback signal. Difference between ideal open and practical open. Infinite open loop gain in the case of ideal operational amplifier. Practical, yes, we will have some infinite gain. It is not possible. Similarly, in the case of ideal, we are having an infinite bandwidth, which is not possible in the practical, because bandwidth is nothing but the difference between the frequencies. Similarly, ideal op-amp infinite slew rate. Slew rate is nothing but if you're giving input at 7:15 a.m., you should get an output at 7:30 a.m. 15 seconds is okay. But ideal op-amp is infinite slew rate. Certainly, you are immediately getting a response, so that is not possible. So we are having a finite slew rate. Zero input offset voltage, that is not possible. That is not possible in practical op-amp. Zero output impedance, again, not possible in a practical case. Zero noise, yes. There are three things I want to discuss. One is harmonic, one is noise, one is distortion. We are talking about noise only. Similarly, CMRR infinite, it is not possible. So where we can use a operational amplifier, we can use our operational amplifier in various cases. I'm coming back to. So we were discussing that this application operational amplifier it can be used as integrator, instrumentation amplifier, oscillator, filters. This is the equivalent circuit operational amplifier. Please note it down. We are giving two input signals, two supply voltages, and one output. So it is nothing but V1 minus V2. So what we discussed what operational amplifier is all about. What is the difference between both of them? This number can be asked, but the pin diagram is very, very important. Right? Without pin diagram, it is very difficult to explain the operational amplifier. What we discussed about the parts of operational amplifier, but now let's discuss about characteristics of operational amplifier. Right? The properties or characteristics of operational amplifier. So we will discuss about it. Let's go back to the slideshow mode. So what we were discussing characteristics of operational amplifier. So yes, they are referred to be linear devices. And to a certain extent, yes, they are linear. So one thing is very clear to you. Somebody can ask you, operational amplifier is a linear device or non-linear device. So you can say it's a linear device, right? So it's basically a voltage amplifying device, 3-terminal device, 2 inputs, 1 output. Yeah? Input offset voltage, it has to be very minimum 6 millivolt we are targeting, but it should be 0 in the case of ideal. So if we talk about input offset current, it is IB1 minus IB2. That means the difference of the current at the two terminals, right? Very, very minimum 200 nanoamperes. Input bias current, it will only come into the picture when you are having two inputs and both are given. Clear? So we will take an average of two currents. That would be known as your common input. Open loop voltage gain, that is differential voltage when open loop configuration. Then we will talk about. There is no feedback. Common mode rejection ratio, gain, we discuss it. Remember this formula. This is very, very important. AD upon ACM. Now, what is AD? Differential mode gain. And what is ACM? Common mode gain. Common mode gain will come into the picture when you are taking an average of two input signals provided. And AD is nothing but a voltage gain that is taken care as an output. Right? In an open loop. In a closed loop also, but we are talking right now in an open loop. Output voltage swing. This is again very important. The op-amp output voltage gets saturated plus VCC minus VE. They are positive and negative voltage. So the voltages can be 13 volt or 15 volt. We are targeting a swing of plus 13 to plus 15 volt. Output impedance, know very well, it has to be very minimum, but in a practical case, it can't be. So we are having a range of 10 to 20 kilo ohm. Input impedance has to be infinite in the case of ideal. In the practical, we will say, no, it is not possible. We will have some input impedance, but depend upon the amount of current flowing through it. Bandwidth, you know very well what is bandwidth. Bandwidth is nothing but the range of frequency from one point to another point. So in ideal case, it is infinite. But yes, we are in a position to amplify any signal from DC to highest AC frequency without any losses. That is your bandwidth. Okay, so frequency response can be infinite in the case of ideal, but in practical, it is limited. Okay, so in short, if anybody asks you what is bandwidth, so bandwidth is nothing but a gain bandwidth product is nothing but a frequency where our amplifier gain becomes unity, maximum. So offset voltage has to be 0 because it is a difference between two voltages. Otherwise, it has to be 0 at the output level. Slew rate, I already discussed with you. That is rate of change of output. That means maximum rate of output voltage, right? So when you're giving input and when you're getting output, that is the difference between both of them. That is slew rate, the rate at which the output is changing with respect to time. Then we are having, this is very, very important, ideal voltage transfer curve. It is basically, you can see we are having a graph between VD and V naught. VD is basically VD is a voltage, right? And definitely it is drawn between VD and V naught. So VD is nothing but input voltage and V naught is nothing but the output voltage. So you can see the positive saturation and the V saturation would be less than VCC, right? A supply voltage. And in this case, if negative V saturation is less than minus VEE, because we have two voltages, plus VS, minus VS, so they are showing plus VC and minus VCC. So let's talk about operational amplifier now. I don't know why it is happening like this, but it is taking unnecessary things. Right? So we will talk about operational applications of operational amplifier. So we can use an inverting, non-inverting, unity gain, summing, subtractor, active filters, and Wien bridge oscillator. So remember this. We will study all this in our coming sections. Thank you. I hope everybody is clear. If somebody having any kind of doubt, they can reply in our comment section. I hope I'm not going very fast. Yes, please tell me. As a continuous previously with the characteristics of op-amp, we're going to start with the open loop and closed loop configuration, right? So we will go with the open loop closed loop configuration. So how can we see what are the formulas? Open loop closed loop configuration, you can see. We will come with the concept of differential amplifier that was already discussed with you all. So a high gain differential amplifier, we know very well perform any kind of operations. The three types of open loop configuration: differential, inverting, and non-inverting. So we will see both. First, we are coming across differential amplifier, in which can note down the formulas. If we are taking V1 as a V input 1 and V2 as a V input 2, so total V output would be gain of V input 1 minus V input 2. That is your differential amplifier, in which I am keeping my input resistance maximum and output resistance minimum, not zero, not infinite, maximum and minimum, right? So if I talk about inverting amplifier, you can see V naught would be minus of AD because it is going 180 degree out of phase. So it will minus AD V input, where AD is nothing but a differential gain. But the output would be totally out of phase. You can see positive is being grounded and negative is being active. So that way it is known as inverting amplifier. Right? Similarly, when I'm talking about non-inverting amplifier, I'm keeping my positive active, right? Positive active and negative grounded. So it is known as non-inverting amplifier, where which the output gain, output voltage, nothing but AD into V input. So AD is a differential gain and input is a voltage. In a closed loop, we are having 4 inverting amplifier with negative feedback, non-inverting amplifier with negative feedback. But whenever we are giving positive feedback to both of them, it will become an oscillator. So remember one thing, whenever the amplifier is giving positive feedback, it will work as an oscillator. Whenever we are giving negative feedback, it will work as an amplifier. First is inverting amplifier with negative feedback. You can see I'm connecting a negative feedback. It will become AB is equal to minus RF upon RI, because over here the input out this RF decide, because if R1 value is 1 kilo ohm, it would be 10 kilo ohm. So 1:10 has to be decided as a amplifier or feedback circuit. Similarly, with negative feedback, non-inverting with the negative feedback. So non-inverting now positive is given, negative feedback. So negative has to be connected with the RF. This RG is an earth resistance. We can avoid it, but that's why known as negative feedback, because it is connected to the inverting terminal, right? Similarly, these questions can be asked for inverting op-amp output voltage. Yes, out of phase. For non-inverting is in same phase. Closed loop configuration. What kind of feedback? There can be positive, there can be negative. In open loop configuration, there is no feedback. So this question can be asked. I hope you understood what actually oscillator is, what amplification is, how can we convert our op-amp into an oscillator or an amplifier. As we already discussed that we are targeting the different characteristics of operational amplifier, and we discussed how the amplifier will work as an amplifier and an oscillator. So let's start now with the inverting and non-inverting amplifier. So you can see the voltage supply is being changing over here. That's why my video was like moving like this. Anyhow, so let's move to inverting and non-inverting amplifier. So inverting amplifier already discussed, and inverting operational amplifier or inverting of op-amp is a type of operational amplifier which produces an output out of phase with respect to its input by 180 degree. This means if your input is positive, output will be negative and vice versa. Similarly, you can see that virtual earth summing point is being connected. Virtual earth summing point where the feedback resistance is connected. So our input, it is connected to the ground, and virtual summing point is where the feedback resistance is connected to the input terminal. Construction or input inverting op-amp, we know we have to make feedback signal at the same potential with the 0 volts or ground, then the junction is connected to virtual earth. You can see the virtual earth where it is going 0. This is your virtual earth. Okay. And virtual earth node input resistance equal to the value of input resistance. So what is the value is coming out to be? Differential input voltage 0 if V1 and V2 is 0. So one thing is very clear. What is virtual earth? When your input voltage is both input terminals has to be 0. Working on inverting operational amplifier, assuming the operational amplifier is an ideal condition, you can note it down. Very, very important. Gain is nothing but minus Rf upon Ri, that is V0 upon Vi is equal to minus Rf upon Ri. This is very, very important. We have to check it out. Please note it down. And then if we talk about AV upon minus Rf upon Ri, you can see the voltage gain of inverting amplifier is decided by the ratio of the feedback resistance to the input resistance. So you can see I'm giving input voltage and it would be amplified to a higher voltage in the both sides, So keep remember positive and negative values would remain same. Advantage is it follows the negative feedback. The gain factor is very, very high and output would be out of phase, potential both terminals maintained and 0. Disadvantage is gain is high, but the feedback is followed, has to be distortion less. And input signal should not contain any kind of noise. Application as the output generated also out of phase, practically used in the application of integration, must be balanced, concept of mixture. So these things are very, very important in the case of application of inverting amplifier. Let's talk about non-inverting amplification. So non-inverting, we know very well the output would be in a phase with the input. Output is a non-inverting. Non-inverting amplifier can be anything. Okay, anything means it has to be connected to the positive terminal. So positive terminal is connected. Now I can ask you what kind of feedback I am providing. It is amplifier, so we are providing negative feedback. In non-inverting amplifier, the input terminal is grounded definitely, and non-inverting terminal will be active. Working, you can see that AV is equal to 1 plus R1 by R2. Just applied KCL. Just apply the KCL at an inverting mode. So you can see V1 minus VO divided by R2 plus V0 minus 0 because it earth upon R1 is equal to 0. So you will get an equation V0 upon Vi is equal to 1 plus R1 by R2. So R1 is nothing but feedback resistance. It can be in a case of non-inverting with positive feedback also. So 1 plus R1 by R2, you can check it out. Advantages of non-inverting amplifier, you can see the output signal is obtained without phase inversion. Whereas in comparison to that, we are having non-inverting amplifier, the voltage gain is very, very variable, right? Disadvantages, more stages are utilized on the requirement of achieving desired gain. They are the disadvantage non-inverting amplifier. You can use in various cases the respective cascaded circuits in gain considerations. These non-inverting amplifiers are used. So what we discussed about advantages and disadvantages of inverting and non-inverting operational amplifier. We also discussed how the operational amplifier work. what is positive feedback and what is negative feedback. In coming topics, we will take care of summer and summing and subtractor with their formulas and compare it. Right? So any comments, any doubts, you can write in the comment section. These are very, very important. So 3 topics are left now. We will go with this adder subtractor. You can see that right now it is not working properly. See how the video is moving. It is why? Because the voltage is we are not getting the same voltage as required, right? So let's say adder and subtractor. We will have a introduction to adder and subtractor. So we will discuss introduction to adder as amplifier and a subtractor as amplifier. So let's see. In this case, op-amp is used to design a circuit. Like right now, I'm using some door. You can see the voice of the door. I'm using LDRs and SCRs over here. So it will take time. Otherwise, I cannot do that. Okay, fine. So coming back to the topic now, introduction to adder. Op-amp is used to design a circuit whose output is sum of several input signals. So it would be added. It would be added at an input signal, right? So that's why it is known as summing amplifier. So output amplified is 1. You can see, you can note it down. Various number of resistances are connected at a negative terminal. So when it is connected at a negative terminal, that means we are dealing an adder in a inverting mode. So we are connecting many resistances at the inverting mode. So feedback resistance is 1, but the input resistance are many. So we will get only one signal as compared to the input signal. So you can see over here, it's a adder where they're connected. Non-inverting is connected to the ground. Virtual short concept. So we are giving where the V1 and V2 has to be 0. So if n number of input terminals are connected and they need to be connected in parallel, otherwise how you will add them, right? This is the first condition, that all the input signals has to be in parallel. You can see I take the current I1 plus I2 plus I3 up to IN. So we can take out V1 minus 0, V2 minus 0, and so on. So formula, remember this formula, V1 upon R1 plus V2 upon R2 plus V3 upon R3. So the formula, what the formula will become? The formula will say the output voltage, because we will create the current. Also, the V0 would be negative. This negative point is only coming because we are dealing with inverting mode. So V is equal to negative of Rf upon R1 V1 plus Rf upon R2 V2 plus Rf upon R3 V3. If it is a non-inverting mode, the formula is 1 plus Rf upon R1. So it would be 1 will be taken out and it would be binomial theorem. I hope this is clear to everybody. If any doubt, you can write in the comment section. Applications of adder, we know very well. It is used in arithmetic logic unit, high-speed multiplication, advanced microprocessor design, and digital signal processing. Now let's talk about subtractor now. What subtractor is? It is basically designed for the difference of 2 input signals and reject any signal if they are same. I hope you understood. See, we are giving 2 input signals at V1 and V2. If both are same, the output would be 0. But if you want to subtract, so that means V1 minus V2, it is quite simple. So you will see V1 minus V upon R1 is equal to V minus V0, right? So you will get the formula V0. See, now we are using this subtractor. If I going back, you will see I am having positive also, I am having a negative also, inverting and non-inverting both. So V0 will be 1 plus R2 by R1 into V, that is nothing but V1 minus R2 by R1 V1. So this is your formula in which we can calculate our working of subtractor. So if you will solve all this, you will get V1 is V2 and then V0 is 0. The formula would become, this is our subtractor, V0 will be R2 by R1 V2 minus V1. It is when the resistances are in quick proportion, that is R1 by R2 is equal to R3 by R4. This is very, very important and very what I can say, very important in fact. So we apply nodal analysis and we get the formula R2 by R1 is bracket V2 minus V1. The application we got, attenuate the radio audio signal and increment decrement operator. So this is what we understood in this. We understood that how the operational amplifier can work as an adder, can work as a subtractor, and how we can use multiple input and output terminals in such a way that the positive and negative feedback remain intact. So now we are left with only one topic. I hope everybody is clear till this point of video, and we are left with only comparator. So any kind of doubt you can write in the comment section. So let's discuss now. You can see how it is going on. So let's see comparator, in which we have to see that how the comparator work and what are the condition, permutation, combination on which comparator can work out. Right? What is comparator basically? A comparator is basically, as the name suggests, it is comparing one reference value with a compared value. This is your comparator, right? So that means construction of a comparator we will decide. We will see how it will work. So as the name suggests, op-amp comparator will compare one analog value. Analog value means one reference value with the existing value, and one value is given as V reference, and output will come on the basis of comparison enough, right? Two values, and will tell it is like a program. Two values the op-amp will compare and give and tell us which is the highest value, which is the maximum value, which is the highest value out of both of two. So you can see I'm giving two values, V reference and V input. So plus V minus V are given. So we will see that which value is more higher than the other one. So comparator basically having its application where we have to find out which value is higher. Okay, or we can say that if one value is having 0, other is having more than 0. So we can say yes, the high gain goes to infinity and output into the saturation. So with the open loop configuration, this comparator having a very good significant when we are working op-amp in an open loop configuration. As you can see in a comparator, it's very, very important. See, you are having a waveform in this V saturation. So it will come positive when it is more. So you can see the output of a comparator will be seen as a clipping circuit. Okay, so it will be positive when the input it will be positive when input voltage is greater than reference voltage, and negative when the input voltage is less than the reference voltage. So comparator we will have as an inverting amplifier. As an inverting mode we use as a comparator, and we also can use comparator on non-inverting mode also. So let's see, this is comparator as an inverting amplifier. What we did, note it down. We are using operational amplifier. We are giving two inputs. One is in this, one second is again with a supply. We are connecting R1 with a protection diode so that the current should not flow. Like you can see the current will flow to this end, but not to this end, because your diode is a unidirectional element already discussed in the AC/DC circuit video. And this is the working of a comparator as an inverting amplifier. You can also see to it. 0.7 minus 0.7, and we can keep one value as a 0.7. Below 0.7 it would be negative, above 0.7 it would be positive. So again we are discussing compared to non-inverting amplifier. It can be done as a non-inverting mode. So see to it, exactly the same. Two diodes are being connected. Instead of giving the voltage to inverting inverting point, we are giving the voltage or source to the non-inverting mode, so that the voltage will go to the saturation. We will take VRF and minus VRF. Again, in this, the output voltage will go to saturation if your input voltage is less than the reference voltage, otherwise it will be positive. So what we discussed that yes, what is application of comparator? It can be used as a sensor. It can be used as a digital communication receiver. Certain codes are being developed, like Henning code, like BCD code. They are being developed on the basis of operational amplifier characteristics. So what we studied in this video about operational amplifier is that operational amplifier is able to perform mathematical operation. It's also able to perform the operations which are good in for the digital signals processing or discrete signal processing or analog even signal processing. So this op-amp, what is the significance of operational amplifier? It is one-in-one amplifier which operate with very less voltage, which can perform all the mathematical operations and capable of integrating multiple functions into one. So that this was of operational amplifier. That's all from my side. If anybody having any kind of comments, they can reply in a comment section. Students, I just want to make sure one thing. I make AC/DC circuits, video machines, video and open video only for your benefit so that you should learn something. So see the video till last. But if you still want a video to be divided or split out, you can just let me know. I will split it out and will share again. But the objective is very clear that you should learn something from my knowledge and implement in your projects or implement in a real time. Thank you. Thank you very much. Have a nice day. Have a nice weekend. Thank you.